So I want to show you today some examples of how we can apply machine learning to electron microscopy data. Especially I would like to focus on these two examples. How we can perform dimensional reduction and also how we can improve signal-to-noise ratio. So first of all, these embeddings I just found it like 3 years ago because in some parts I have some experimental data here on the top and then I have simulated data. But you can clearly see it's difficult to compare them. You cannot compare pixel by pixels because you have to calibrate the dot, you have to recenter, you have to denoise. So what I just found out reading something is called one-shot learning, in which you take an image and do some dimensional reduction. Actually, you're extracting some specific features of the image. So I wanted to do that. So we wanted to find a way how we can compare simulation with experiments. That was one reason why I wanted to study embeddings. Another reason is you can see this nanorod. This is a 4-dimensional stem, and this is a virtual stem image here. And this is different virtual stem. Here I just calculate the scattering cross-section, which is actually the intensity for each atomic column, plotting against the number of atomic columns. So you can clearly see that the red one is experimental data, and the blue one is the simulated data here. And you can see that experimental data doesn't match to low angles with the simulated data. We can only match in one region, but then all the other regions are wrong. So that could be to different effects. Can be due to carbon contamination, also can be due to plasmon and so on. So then I just thought that maybe it's better to create some kind of algorithm that is not actually intensity-based, because this scattering cross-section is intensity-based. So it's better to create something similar, but it has to be feature-based. So first we have to start and try to answer this question: how we compare two diffraction patterns. Okay, we know first that the data is noisy. We know that this pixel-wide comparison won't work, and also experimental CVD change with dose, rotation, and homogeneous scaling. Low-angle scattering, as we know, is sensitive to bondings and also contamination and so on. So then is the dimensional reduction, actually something called embeddings. In that case, you want to take an image and only just output a set of numbers. But the problem is we don't know the grand truth of this set of numbers, so we cannot do this classification. This is another way we can train this. Because it's a normal class, you want to do some kind of regression, you need to know what is the grand truth. We don't know the grand truth. In that case, you can use something called contrastive loss. In that case, you are able to compare similar examples and completely different CVD patterns. And the neural network by itself is going to generate what is the embeddings. This is the loss function. In this case, you just give here an anchor, and here you can give the positive example here. And then you're going to take the Euclidean distance of the embedding representation. And there are positive examples, they are similar, so you have to minimize that one. If they are not the same, so you want to maximize, you want to push away this vector representation. So this is taking 2 examples, but then you can go further. You can take 3 examples, for instance. In this case, you're going to take an anchor, a positive and negative example. It's the same neural network. You're going to send the diffraction, 3 different examples of diffraction pattern. You're going to get a vector representation. The idea is to try to minimize this distance between them and trying to push away between this and this. That is actually, this is what the triple loss is doing. So one key parameter here in the embeddings is first, the number of dimensions we need to represent this data. Another one is how much you want to push negative examples from each other. And then, because I'm a physicist, then I want to put some constraints, because I want also to encode another information about thickness there in the vector representation. In that case, because I'm going to use simulation for the training, so I'm going to say that vector representation has to be proportional to the thickness difference of these diffraction patterns. Another thing to avoid this kind of actually wrapping around, we can say that the norm, if one CVD pattern have a higher thickness, then the norm has to follow, I think, the same. So now the question is, what is a positive example? You want to say this is equal to this. So first I say that diffraction, these positive, they are invariant to those. They're also invariant to the fine transformation like rotation, homogeneous scaling, shifting. They have to give you the same vector representation, also occlusion. You can just remove some data still. It has to be strong to that. Yeah. And also, for positive specimen, we have to train it with different nanostructure, specimen ages, weight, and so on. So here we use real simulations. We simulate like almost 100,000 different simulations here. You have to simulate the specimen tilt, carbon contamination. That is still going to be a positive example. I can tell the diffraction pattern, I can tilt a bit, and then they have to be the same. This is, for instance, one of the structures I simulate here. I just put the probe here. I run a simulation that I can simulate the CVD. And also I simulate a wedge and so on. Also simulate tilt here in this case, small tilts. Okay. And so I took different FCC crystals and also some random specimen. And with different, also, this is only optimized for, actually for aberration corrected microscopes. Also include different source size broadening, the focus spread. The simulation has to be quite accurate because it's going to be feature based, this one here. Yeah, this is some samples I simulate for different orientation with the random specimens. Two orientation, different root mean square displacement and so on. So then we just use an architecture. In this case, I use one of the recent architecture, which is called the EfficientNet from Google. I use the version 2. It has just few number of parameters. We're talking about 5 million parameters because the previous neural network have like 60 million, the AlexNet, so it was quite, you can have a lot of problem with overfitting. They were not quite efficient. This one is actually, the inference is really, you can do in CPU, is quite fast. And so the first row, here is my anchor. This is going to be my positive example. And you can clearly see how this and this are the same. They're only a bit rotated, they can be a bit shifted. They can be with different dose, each one. And the other one is a completely different example. That is actually coming from a different thickness of my diffraction pattern. So then I train it. And so now I can have a vector representation here. If I now give to the neural network this diffraction pattern, because are the same, they have to give you the same vector representation. You can see the red one here is the vector representation of the anchor. The blue one, the vector representation of the positive example. And the black one is a completely different diffraction pattern. You can see the blue and red one overlap each other quite well. And the black one is far away. This is another example, for instance, here. You can see here, still we have the same one. So it seems to be the neural network is working quite good for simulated data. And then because I constructed with this constraint, physical constraint, now I have something similar. Maybe some of you know about the scattering cross-section, which is the intensity in each atomic column, more or less. And now, if I take the norm of that vector representation, this is what I have. And I found out that this norm is actually invariant to different source size broadening. This is quite similar to the scattering cross-section here. So, okay, there's a lot of detail here, but yeah. We are going to show you just with experimental data here. The experimental data, first of all, this is how experimental data looks like. The data is quite noisy, the data. You take this pixel here, the blue one, you can create some virtual stain image. You can create also a ring here, you can create another virtual stain image. You can see the data is quite noisy. So one option I wanted to use was the PCA. You can clearly see if I take only 20% of the component, you can see I can increase the signal to noise ratio. But then I can take 15, I can take maybe 7.5, and I don't know where I have to stop. But you can see features start to change. You start to use different values of PCA, how many components you are keeping. So in that case, it's not actually recommendable to use PCA because you are changing the features. The data is not quantitative anymore. So another approach to increase the signal to noise ratio was to use column-weighted average CVD. So in that case, this is my 4-dimensional data. So I just take all the diffraction pattern around this, and I'm going to average with a Gaussian envelope here. So I can go from that pixel, I can apply this mask there, I average all the diffraction pattern, and then I can have something that is representative for that column here. You see the signal to noise improve a lot, but it's quite localized, only column-wise. Now we tested this experimental data. This is some experimental data of gold, we know it's gold. And then we wanted, so when we apply this kind of atom counting on these examples, we couldn't get any consistent results. So now with the feature-based vector representation, now we can perform atom counting, because now we can compare directly with simulations. It's independent if you have carbon contamination, you have plasmon, because carbon or plasmon are going just to change the intensity, but they're not going to create new features on the CVD. For instance, have a look here. This is the vector representation of all these. I took all these columns here. I generate CVD pattern, average CVD patterns, and then I send to the neural network. And this is the vector representation here. And this is now, I take the same parameters, I run the simulation, this is the simulated data. You can see that it looks quite similar. Now I can do just a match 1-to-1. You can clearly see now I can assign number of atoms. And this is the 3D model we can get from this data here. Before, when we use this kind of atom counting based on intensity was failing. It gives you some no sense result, especially for low angle. That is why people don't use atom counting for low angle regimes. We also tested with another data set. This is still a sample. I think this is platinum, I think. And then we ran a neural network. We can clearly see they have the same or similar vector representation for experimental data and simulation, and it's quite easy to assign, the number of atoms here. So now we have a tool to do CVD comparison with simulation with experiment. Even you can do some kind of atom count if you want. So you have several applications of this. This is just one of the possible applications, but because I want to show you several examples, so I don't want to go in quite deep detail about that. So I want to show you now another approach. Actually, you are doing in the Rosalind Franklin Institute is about the CVD restoration here. So the idea was to run several simulations, minimal simulation with different solvent, different structure, because we're only mostly working with here biological samples here. So we are trying to simulate more or less quite accurate. In that case, so diffraction, we want to create a neural network here that you send a noisy diffraction pattern, go to a neural network, you restore it because they are simulated, you have the ground truth, and then you're also going to improve the data. When you go to low dose, you can use a discriminator there. That is an optional, but I also use discriminator. First of all, what is one important is which architecture you want to use, because there are several architectures. You can create your own architecture, but there is some efficient architecture when you just reduce the number of parameters, you avoid overfitting and so on. This 2.5 million of examples seems a lot to you, but actually was shown last year and a few years ago, that the difference, you train a data set with 1 million of 12 million, you can get a big difference. So actually you can get better results, you increase your data to order of 10 million of examples. So we can run more simulation. All the simulation in the Rosalind Franklin Institute using the supercomputer took 2-3 weeks, something like that. So about the architecture, maybe you know this. This is a competition called Entire Image Challenge. You can find, it's a competition, worldwide competition, when people actually submit their architecture for a given challenge. You are trying to do whatever of this kind of task. It's better to look into the paper and you have all the best architecture. Maybe you have just to fine-tune, especially for your work. For instance, this is one of the best architecture here from this challenge 2019, this 2020 here. The difference between this and this is for image restoration. This is image denoising here. Also, both are image denoising. But this actually runs faster here. And also, this is actually works quite good if only you have temporal noise. But this can work also for temporal and spatial noise. So this is two architecture here. And then I train the neural network, so I run a lot of simulation, multi-slice simulations.
Can I ask a question?
Yeah.
What's the difference between temporal and spatial noise?
Yeah, spatial noise is when you correlate the noise, the one pixel depends of the other local pixel. For instance, The other temporal is only just the Poisson or other one thermal noise, only changing within the pixel. Okay.
So spatial is spatially correlated.
Yeah, spatially correlated. Sorry.
Thank you.
Yeah. Here, for instance, then I trained the data, so I have to retrain several times to tune the parameters in order to have. First, you have to study the noise, the different sources of noises. Here, you have to model all noises in the CCD cameras. The noise model is going to be quite different for normal CCD camera or for you have actual direct electron detector camera. And then this is let's say my input data, this is my ground truth, and this is my restore with the NCVD here. And this is you use another image restoration here. I'm going to explain maybe later. you can clearly see what you actually do for a specific task actually give you much better restoration if you compare with the ground truth, compare with this one here. So this is one of the few examples here. You can see different, these are actually, okay, no, this only has this second column, we don't need it. You have to compare this column, well, this is the prediction, and this is the ground truth here, and this is the difference here. You can clearly see actually our prediction looks quite similar to the ground truth. But as I will say, you have always to test it with experimental data. Because with experimental data, you have to fine-tune all the parameters of your modeling. And then you're going to learn if your modeling of the noise is correct or not. For that, so I went to the paper they published in Rosalind Franklin like a few years ago about the rotavirus. And then so I used the IPAM algorithm, but in that case, I just processed the raw data and also process the data without with the restored data. So here you can see the raw data. This is the modulus, and this is the phase here. This is what we get from the data. And you can clearly see, you have to see some kind of features. It's quite good because this is working quite good because the dose is quite high here. It's around like 30 electrons, 22 electrons per nanometer square, something like that, or Armstrong square. Yeah. So, and this is the data. If you just do the same algorithm, but using the restored data. And you can clearly see there is not much difference here. Eh? It's almost quite a small difference. You can say, okay, why I need to restore the data if I can get the same with using the raw data? But the thing here is, because you have so much data, you have so much oversampling, you have also here like a 90% oversampling. That is why you have that option. But we can actually, what we can do to see it, yeah, this is online profiles of the data. You see they're consistent, only the noise a bit reduced. But what happens, you're going to jump 2 pixels. So now we're going to use only 25% of the data. So we want to reduce the overlap. Have a look here. This is a video. Should play. It's a video. Okay, no. This is only using 25%. This is using the raw data. Have a look at the phase, how it looks like. And have a look at the phase, how it looks. You can see the restored data gives you much better, a bit better. And yes, you see the light profile consistent here. But you can go even lower. You can say, let's try to use only 6.25% of the data. And this is using the raw data. And this is using the restored data. You have to see a clear difference. So here the overlap here is quite small, like around 10%. So an interesting part of the restoration, also when I compare here, I ran like a 40 iteration. I found out that when you use restored data, you need actually less iteration to converge. For instance, I will show you here. This is a video. Here is the modulus and phase using the raw data, and this is modulus and phase. This is modulus and phase using the raw data, and this is modulus and phase using the restored data. You can clearly see, just focus on this one, that after 4 iterations here, this doesn't change anymore. This one here, this doesn't change anymore. You get stable. But if you compare here, the noisy data is changing all the time. So you need a huge number of iterations to have good results. So with 4 iterations using the restored data, you can have very good results. Then there's a light profile here. So then we wanted to go, because what I showed you was actually quite high dose, was around almost 23 electrons per square Armstrong, something like that. So in biology, they want to reduce the dose. So they want to go, their dream is to go 1 electron per square Armstrong. So see, here actually there are an example, it was published in the paper from the Rosalind Franklin, with different doses. This is for the rotavirus. You can clearly see how the signal is degrading here. We have 22, 11, and 5. It's quite difficult to see here the rotavirus here, or to get the feature, some kind of high resolution features. So, and I found out that, so I wanted to apply for the data, the restoration. And here, this is my raw input, and this is my restored data after passing through the neural network. So the problem here, you can see that the diffraction path is not centered. So now you have to recenter. How people were recentering, actually, they are doing a threshold and then trying to find a geometric center here. So this is a video, I think so. Yes, you can see here in live. So how it's changing here, Because you're thresholding here on the raw data, the geometric center is going to change a lot. But the restored data is more or less going to be more or less stable. You can clearly see it here. Here we calculate the geometric center using the restored data in the red one. You can see more or less good, and the blue one using the raw data. You can see how it's changing here. That is going also to affect the quality of your reconstruction there. And then I took few lines there. That's how it looks for different few lines. Even using the restored data, you can clearly see that it still is, we cannot determine quite accurate the center of diffraction pattern. But anyway, so then I combine this threshold with also using the phase correlation method to recenter all the diffraction patterns. This is what I get. So this is the result from the paper. And remember, this figure is quite difficult to see the rotavirus. And this is the same one, but using the same data, it's the raw data without any restoration. The only difference here, I use a better alignment of the CVDs. So I recenter the wrong kirans better. You can clearly see here to see some kind of high resolution features here. You compare with the published data here. It's the same data without restoration, but only recenter better. So using phase correlation to recenter the data. So now, then I just, now run the neural network, and this is a result from the neural network. Something interesting to see here, you can see this dark region appearing around here. Actually, I found out it's coming from the Poisson noise in the restoration process. Because how you're using the IPAM algorithm, you're replacing the square root of the CVD patterns in the Fourier space. Because a nonlinear algorithm, you put more iterations, you have to create this kind of dark regions here. You can clearly see here, it looks like the contrast start to, you go to lower dose here, you have a higher contrast, which is a bit weird here. You can see this a lot of variation compared with the background here. So, but then if you use the restored data, you have almost consistent result here for all different doses. What it should be, it shouldn't change with the dose. It should be mostly the same. So, but then it was working quite good, this neural network. But then I say, okay, we can do much better than this. So we can also do the restoration, but also recenter automatically using one neural network. So, and this is what I did. So you can see now the CVDs are off of the center, this one here. And the neural network is learning also to do restoration plus recentering. You can see here. So we train, we do all the stuff, but quite important here is before in the previous one I was using this architecture here. And now I'm using this architecture. As I told you here, this architecture has some kind of like a skip connection here. It means adding the data is passing information from here to here. That is, so it's going to learn only the difference. In that case, because the data is shifted, it's better not to do that. It's better to use something like this. You do here concatenation, you're not adding. So I also remove this, I'm removing also the adding. I make some kind of modification of this neural network. So I remove these layers. I only have concatenation here. And with that neural network now, these are the new results here. This is data published from the paper. This is the raw data using a better algorithm for recentering the CVD pattern. This is the previous neural network, and this is the new neural network now. This neural network is still under training, so the result might improve. You're already hearing 5 electrons per square angstrom. I'm pretty sure if we just generate more data and I find a better architecture playing with fine-tuning the hyperparameters, maybe we can get, and combining different CVDs, we can get maybe to 1 electron per square angstrom. So this is the most of the, I still have time. Yeah, okay, this is, yeah. So this is just 2 topics I wanted to show you, but there is also more work we've been doing actually at EMAT in the Rosalind Franklin Institute. For instance, I can show you something, yeah, I call it in previous, I call it NEMAT. This is stem restoration data. So in this case, you have to understand how you're collecting the data here. So data, you're collecting data in raster scan. You put a detector here and you just build pixel by pixel your data. So that's going to create different kind of distortions here. You can have jitter, fast scan distortion. We spend a lot of time trying to analyze data, how to model correctly fast scan distortion. Detector noise, jitter, white jitter, thermal noise, downsampling, some different kind of noises, a combination of different kind of noises here. So then I used quite similar to the previous architecture I showed you here. Maybe here, this one here, something similar. And then I was able to restore data, but I have to fine-tune. I have to always with the time improve my modeling. Because all this neural network was pretty good if you go to high doses or you go to medium doses. When you go to low doses, you have to have problems because it's going to be quite important how you are modeling the physics there. Physics of the detector, physics of the electron-specimen interaction, and so on. So then it took me a few years to create very good models. And this is experimental data, strontium, titanium, and this is what we get here now with the restoration. So there is a lot of detail here how we can keep quantitative data. We want to keep quantitative results. We actually want to get, we do not want to create pretty image, we want to create quantitative data. So we put some constraint condition, like you have to keep the mean intensity, the contrast, and so on. This is another experimental data. This is another particle in a gas holder. This is for one, it's actually time series, but this is one single time series, and you can clearly see how much we can recover now. It's quite one of the most difficult examples, but then you have to create very good model to model all this stuff here. You can see large phase scan distortion. Why? Because here, in that time, we were using this Titan, or the second generation of Titan, it was like at 250 nanoseconds we were collecting the data. But now, this is another data maybe you remember from the paper of Sander van Aert. So now we can actually improve all the previous data using this restoration. The interesting part, you don't have to train, because for training this, I actually used 20 million of examples of simulations. It's a huge amount of data, but now we can work for everything. But then we wanted to go even further. We say, okay, STEM is good, but it's completely different to try to restore an image at high resolution, low resolution, because you have more prior knowledge. High resolution, you see that everything is almost made of round shapes. But low resolution, you can create whatever stuff. So then we create another neural network just only trained with low resolution images. I have to simulate low resolution using several approximations. And this is another example, but I will show you that low resolution later. This is another example. You can clearly see it's quite difficult to see. But now you can easily see all the atomic columns, and even here. Okay, and then not only we create a neural network for high and low resolution, we also create a neural network for high resolution TN and low resolution also for SCN. So we have 6 neural networks, train each one in 20 million of examples. And this is a nanorod. Here for TN, you have to simulate quite accurate dark current noise, because if you want to go to very low dose, current noise matter a lot. Also the detector, yeah, all different kind of noise, you have to have very good modeling. This is what you can get. This is another example. This is where in the limit of the car, almost here everything is dark current noise here, and this is what we can get now. Some results using SCN here. You can see it's working quite good here. And what I want to show you here is, so how much we improve. So this is a paper we published in 2017 or 19, or 17 maybe. In that case, I use a simple neural network. It was 12 layers neural network. And I train with Poisson, with different kind of noises, more or less related to the STEM method. But I didn't have very accurate models. In that case, I use time series. I have to use 5 time series in order to do the restoration and do after that registration, and I can get something like that before 2017. Now with a single image, we can get like that. Much, much better. We can go straight from here to here, one single image. So what is the difference here is only because I include the physics there in the noise distortion. How you model the noise matters a lot, especially when you go to low dose and fast. And now the model is quite good that we're able actually to recover. Yeah, FEI microscope, at least one of the latest generations, or maybe 4 years. You can get actually, it allows you to get the dwell times 50 nanoseconds, the minimum one. But it is quite distorted, the data. But now with a new model, actually we can recover quantitative data. So this is not shown here, so this paper is coming out there. Also the neural networks are going to be open source, so people can use it. It's nothing, you don't have to retrain. You just go and use it, that's it. So another thing is, I wanted to show you another thing is about physics compression. So there is a paper also trying to submit to ultramicroscopy here. So something called a scattering, is something we call it here the scattering intensities here. So for that case, we normally take experiments. We just also normalize the detector of the stem in the stem mode. And then we try to compare with simulation and then trying to count number of atoms. But the problem with the stem, these simulations are quite expensive. I mean, are not quite expensive, but it takes like around 1.5 hours, something like that. You have to have very good sampling, and then you have to do another data processing. You have to do cell replication, unit cell replication, and then also convoluted with the source size broadening. And after that, this processing can take like 1 second. So the total one is going to be around 1.6 hours, even using GPUs. Here you have to use phonon calculation because we want to do quantitative stuff here. And then you can extract from this image what you want to study. You can take the cross-section, you can take the standard deviation, direct comparison, and so on. This is, for instance, the cross-section. This is the standard deviation of the image. So you can take another extra few minutes. So the idea was to train a neural network. We can simulate for the most common FCC specimen, the most common also orientation along the 110 and the 001. And then, so we want to say we give these input parameters of the microscope, and then we want to generate this one here in one go. We don't want to do it in the order of hours. We want to do it in microseconds here. So we did that. I just ran a large amount of simulations using a lot of phonons, full multi-slide calculations. And then I create this architecture. I trained with several architectures to see. Okay, this is the architecture I created. I trained with 16 million of different examples. And now we can do something like called real-time calculation here. Now what we can study with this kind of simulation. So this is the histogram. How is the error distributed for all different atomic elements we train? It's FCC for two different orientations, 110 and 001 here. You can see more or less they follow the same trend. So we did actually very good training here. We use different combinations of loss functions and so on. And now what we can do. When we train neural network, you have to be very careful. People always like to show only the best, and when the network works the best, but it's not the correct way to do it. You have to go to the worst case scenario where the data start to fail. And this is our worst case scenario here. So the red one is the grand true, and the blue one is the predicted one. So what happened here? What you see is still, look at this is the worst case scenario, but it still looks quite good. So what happened here? First of all, you compare the inner and outer detector angle of your stem detector is quite small. It means, I think actually you have to make the neural network much deeper, and also we're going to need more phonons and a better sampling to capture all this information here. This is for the 001 orientation. This is the worst case scenario for the 110 orientation, something similar here. And what happens if you go here? Take some examples about here in the average here. We are here in the border. Now we go some examples here. This is how it looks like here. They really overlap in the full range here. With that, we were able actually to compress all the physics, in just in a small network. These networks only have like a 1.7 million of parameters, something like that. This is for different, let's say, zone axis orientations here. And with that, you can do different kinds of studies. You can change all of them in real time. You can optimize the parameter here, for instance. Most of the time, when people use a scattering cross-section, they only use one simulation. But now, because we have real time, we can actually estimate experimental error. We can put the standard deviation of our experimental error, and we can also see how much it's going to affect on the scattering cross-section here. You can clearly see that when you are in 14 specimen, you don't have overlap. When you go to thicker specimen, you can have overlap between the number of atoms and the scattering cross-section. Another one you can use for optimize. You have your experimental data here. And so you can run optimization in order to try to match the experimental scattering cross-section curve with the simulation here. Also, we did some kind of work in compressed sensing here. I'm going just to go quite fast. So we also did compressed sensing. Yeah, we generate also a lot of simulations here. We train a neural network. The interesting part, we actually use different kind of random mask. The first random mask here is actually fully random. You can clearly see, take the Fourier transform, looks like that. Has to be white noise here. You can see white noise. And the second random mask, so I'm going to skip one pixel. I cannot have two connected pixels. It's going to be random. I cannot have two consecutive pixels in the x direction. In the third one, I cannot have two consecutive pixels in the xy direction. You can clearly see here, you see this kind of band here, and when you have this third constraint, you have like this. So when you use this kind of compressed sensing using the Fourier or this kind of the cosine transform or other transform, more or less it has required the data has to be random, the sampling has to be random. But with neural network, it's not a requirement anymore. I can show you here which one. So I trained 3 neural networks using the same data, only different masks. Look at what we get here. You use fully random, you get something like that. This is the error. Maximum error, the minimum error you can get. You use this kind, skipping one. You cannot have 2 consecutive pixel samples. You get something like that. You put a third constraint, actually you can have a lower error. It's the same, keeping the same number of sampling points. So this was like a 20%, I think, keeping 20%, but only changing the different kind of way how you are scanning. You can have you can have a much better results here. The interesting part of that, I found out, so I wanted to see what is the best mask. I can use this, fully random, this or this. And then I found out that the random mask, fully random mask is not the optimal. I found out you can get much better if you use hexagonal mask, some periodic hexagonal, because actually you find out it's covering the bigger area. That is quite interesting. The result is not shown here, but yeah. Okay. Yeah, this is the reconstruction. It was quite fast, this neural network. Now we can do it much better using the more recent architectures. We also do some work in jitter quantification in the 4D stem. Normally when you have the data, because you can collect data in 1 millisecond, you're going to have a lot of jitter here. So in that case, you want to quantify the jitter, because if I quantify the jitter, I can apply this transformation to my full 4 data set. So I try just to directly, my first try was to give an image like that. You can create some virtual image using the 4-dimensional data and trying to predict the jitter. It didn't work. Then I found out it's better to do it in 2 steps. The first step, you're going to do a restoration, or you can use some reference. The second one, you're going to take that reference plus the jitter data, and you're going to show what is the output. The third one, you can take this jitter and give the image, and then you can restore it. This is quite, here it doesn't matter, but when you go to very low dose, you have only few pixels, few electrons there. This is going to matter, how you're going to do the interpolation. Here the interpolation doesn't matter. Go to low dose, everything starts to fail. So it's better to create some neural network, because neural network are good keeping continuity between pixels. This is the first neural network, so you do some kind like image restoration using some virtual stem. Second neural network, you combine these two and trying to predict the jitters in XY. The third neural network, you combine the jitter plus your data, and you try to restore it. You do, I think, you can do for all the pixels in your data set. Another way is also something like that. In order to compare with another method, I use the optical flow equation. You can use the optical flow equation. You can also, more or less, under certain assumptions, you can actually get the jitter from your 4D-dimensional data. Okay, this is more or less mathematics, how you can apply the optical flow equation. But I want to show you examples. This is simulated data. So this is my simulated data. This is my ground truth. This is also the, let's say, data contain jitter. My ground truth is a 4D data. And actually, no, here is 2D only. But actually it belongs to one slide of the 4D. This is my difference here. So I'm trying to quantify the amount of jitter. And you can clearly see here, red one is going to be the ground truth jitter. Blue one is going to be the red one is predicted by the neural network. And the blue one is actually coming from the optical flow equation. And you can clearly see the optical flow equation works pretty good. You see the black one and the blue one is almost the same compared with the red one. So I say, why I have to train a neural network to do this kind of jitter if I can use the optical flow equation? But then it's because it's easy here to determine the jitter. But what happened in this example here? If you have something like that, now it's quite difficult to determine the jitter here. Because to determine jitter, you need to have like a contrast there. It has to be some variation between the pixels. And then have a look here. If you apply the optical flow equation, you just get crazy here. Because a set of linear equations, and then you have only pixels, you have noise here. And you can see that the black one starts to get crazy in this area because there is nothing here to compare. And then the blue one gives you consistent result here. It doesn't blow up. It also reproducing all this area here, reproduce quite good quantification of the jitter. Then we apply to the experimental data. We take the 4D stem. We can create several virtual apertures there from the center of the ronchiram until the end of the ronchiram. And I combine all of that and I do some optimization to find out a unique jitter. This is what I get here. It looks quite good. This is the comparison between the optical flow and actually the neural network here. So another example also, we did some kind of atom counting plus composition. In this case, I just ran several simulations for different atomic columns and trying to teach. This is classification to teach to which column belongs. This is oxygen 7, this is strontium 5, titanium oxygen 3, and so on. We tried a neural network, and so we were able to get good results here, although this is only with only with simulated data. Later we find out this doesn't work properly because low angle scattering is quite affected by contamination, also can be affected by plasma and so on. We also use neural network to do high resolution data alignment, especially for tomography. In this case, we have a collection of different images at different rotation angles. This is just we just tested with 3 different orientations, 90 degrees, and we just did neural network to actually output what is the center and the rotation angle here. And then so now I want to show you this is the experimental data, how it looks like. You can see we have to align this data. We only have three projections. How do I align? Most people, how do they align this data in the old times? We're trying to move it manually, because cross correlation is not going to work here because there are different orientations here. So, but then using this neural network, we're able to align. So the neural network output what is the center and how much we have to rotate each image. And then all this can be aligned. Okay, that's it. I can go for more, but I think that's enough. Thank you.